by tracking every single atom inside it.
It's impossible, right? The scale is mind-boggling.
Exactly.
Electrons, protons, neutrons.
All interacting all the time with these really strong forces. It's called the quantum many-body problem.
And yeah, tackling it head on. Forget it. It's like counting sand grains, like you said.
So today we're doing a deep dive into something that gives us a way around that complexity. Quasiparticles.
Ah, yes. Not your fundamental bits like electrons, but these
Emergent things.
collective behaviors.
Right. They basically simplify this incredibly complex picture. Our source today is a really comprehensive look at quasiparticles in condensed matter physics.
A classic topic, but still so much depth.
And our mission for you listening is to really unpack why these things, not quite real particles, are so essential. I mean, for understanding everything from your phone to maybe reality itself.
It's a huge concept. And it's fascinating because, instead of just getting lost in all that microscopic detail.
Which you could easily.
Oh, absolutely. Physicists found they could look at the collective action, how the whole system behaves together. And that's where the quasiparticle idea comes in. It's genuinely one of the most powerful concepts in modern physics.
A real shift in thinking.
A profound one, yeah.
Okay, so given this massive problem, these countless interactions, how did they even start to simplify it? What was that shift?
Well, the big hurdle is just how strong those interactions are. An electron in a metal isn't just floating freely.
No, it's constantly bumping into things, pulling on things.
Exactly. Other electrons, the atomic nuclei, and the Coulomb force, just basic electric attraction and repulsion, it's strong. Often much stronger than other energy scales in the system.
So you can't just ignore it.
You absolutely can't. So the breakthrough wasn't about calculating everything. It was about reconceptualizing. Finding a way to map the complex, messy, strongly interacting system onto a simpler model.
Okay. Simpler how?
A model that acts as if it just contains different kinds of particles. Particles that only interact weakly, moving in a sort of effective vacuum.
Ah, so it's an as-if situation. We're not saying new fundamental particles pop up, but we're looking at, like, disturbances or collective wiggles in the system that act like particles.
Precisely. Emergent phenomena. That's the key idea. Think about, a bubble rising in a glass of beer.
Okay, yeah.
The bubble itself isn't, a new substance. It's just displaced liquid.
Yeah.
Empty space, basically.
Right.
But it behaves like an object. It has a shape, a size, it moves up with a certain speed, momentum. Two bubbles can even bounce off each other. But crucially, that bubble can't exist outside the beer, can it?
No, you scoot out, it just pops. Gone.
Exactly. Reverts to its components. Quasiparticles are just like that. They only make sense within the many-particle system, their medium.
So if you tried to isolate, say, an electron quasiparticle from the metal,
it would just become a plain old electron again. It sheds that dressing of interactions. And something like a phonon, a vibration. It just ceases to exist entirely outside the crystal.
I like that analogy. It makes it clear they're descriptions of the system's response, not fundamental building blocks.
Exactly. And this change in perspective is incredibly powerful, that intractable many-body problem. It suddenly becomes manageable.
Because instead of tracking 1023 interacting electrons,
you're analyzing maybe a dilute gas of these weakly interacting quasiparticles. And that means you can use powerful tools like statistical mechanics, kinetic theory, tools originally made for simple gases.
And apply them to super complex solids. Wow.
It's a game changer.
And here's what really gets me. This isn't just some mathematical convenience, right? It's not just a trick to make the sums easier.
Not at all.
The fact that theories built on quasiparticles make these incredibly accurate predictions about how materials actually behave, that's real proof, isn't it? It's like this emergent picture is necessary.
That's a critical point. It's empirically validated. And if you zoom out, think about the bigger picture. This really represents a shift in, ontology, how we think about what's real.
From just pure reductionism, only the smallest bits matter, to embracing emergence.
Exactly. It suggests that the best way to describe reality might actually depend on the energy scale you're looking at. And remember, the underlying particles, like electrons, they're fermions.
Right.
But these emergent excitations, these quasiparticles, they can be fermion-like too, like the electron quasiparticle, the whole we'll get to. Or they can be boson-like, like phonons, lattice vibrations, or plasmons, electron gas oscillations.
So quasiparticle is kind of a catch-all term.
Yeah, it's a useful umbrella for all these particle-like emergent things.
Okay, that idea about reality depending on the energy scale, that's deep. But how did this intuitive idea, this as-if thinking, become rigorous science? Who nailed it down?
That really comes down to Lev Davidovich Landau, mid-20th century physicist.
Ah, Landau. A big name.
Huge. His Fermi liquid theory from 1956 is the bedrock. He basically solved a puzzle that had been nagging physicists.
Which was?
Earlier models of metals, like the Drude and Sommerfeld models, they actually worked surprisingly well for some things, but they totally ignored the electron and electron interactions, which we just said are really strong.
Right. How could they work if they missed such a big piece?
That was the mystery. Landau provided the missing link. He explained why those simple pictures weren't completely wrong.
Okay, how? What was his key insight?
His central idea is something called the principle of adiabatic continuity.
Adiabatic continuity.
Yeah.
Okay, break that down.
He basically argued, imagine you have a system with no interactions, just free electrons buzzing around. Now, what if you could turn on the interactions really, really slowly?
Slowly, like gradually dialing them up.
Exactly. So slowly that the system evolves smoothly, without any sudden jumps or phase transitions, adiabatically.
Okay. And what's the big deal about doing it slowly?
The crucial consequence is that there's a direct one-to-one mapping. Each quantum state in the simple non-interacting sister smoothly turns into a corresponding state in the complex, interacting one.
Ah, so a basic electron state becomes...
It becomes a Landau quasiparticle state. It's like the bare electron gets dressed.
Dressed.
Yeah, dressed in a cloud of interactions. It's the electron plus the response of all the other electrons and the lattice vibrations around it, all moving together as a single entity.
So this dressed electron, this quasiparticle, it keeps some electron properties, like charge and spin?
Precisely. Landau showed it keeps the exact same charge E and the exact same spin, plus or minus a half. Those fundamental quantum numbers are preserved.
But other things must change.
Oh, yes. The big change is its effective mass. We call it m star.
Okay, effective mass, not its real mass.
No, not the mass you'd measure if you pulled the electron out into a vacuum. It's a phenomenological quantity. It basically wraps up all those complicated interactions into a single number that tells you how heavy the quasiparticle feels as it moves inside the material.
How it resists acceleration within that specific environment.
Exactly. It's determined by the shape, specifically the curvature, of the quasiparticle's energy-momentum relationship right near the crucial energy level called the Fermi surface.
Right, you mentioned that curve, energy versus momentum. Can you give us the non-physicist version again? How does curvature relate to feeling heavy or light?
Sure. Think of that energy-momentum graph again. If the curve bends sharply, like a deep U, a small push in momentum gives a big change in energy. It accelerates easily. It feels light, low effective mass.
Okay.
But if the curve is nearly flat, you need a big change in momentum just to nudge its energy. It resists acceleration. It feels heavy. Large effective mass.
Got it. The shape of its rule book determines its inertia inside the material.
Precisely. And the Fermi surface is just the boundary marking the highest energy electrons occupy at low temperature.
Right.
You look at the curvature there because that's where the action happens in metals.
And you said this effective mass can be wildly different.
Oh, massively different.
Yeah.
Sometimes hundreds of times the free electron mass. And sometimes it can even be negative.
Wait, negative mass? How does that even work? Does it accelerate backwards?
Kind of. Inside the crystal, yes. If you push it one way, it accelerates the other way. It sounds bonkers, I know.
Yeah, that breaks my brain a little.
But it's real within the context of the crystal's energy bands. It happens when the particle is near the very top of an allowed energy range, or band. And understanding negative effective mass is absolutely crucial for understanding the electron hole.
Ah, the whole quasiparticle.
Right, because the hole is an absence of an electron at the top of a band, where the electron would have negative effective mass. The absence itself behaves like it has positive effective mass and positive charge.
Wow. Okay, that's a leap, but I think I follow. What about stability? These quasiparticles, do they last long enough to be useful?
That's the other absolutely critical piece. They aren't stable forever if you isolate them, but inside the material, Landau predicted something amazing.
Which was?
Because of the Pauli exclusion principle, basically, electrons are antisocial. They don't like being in the same state.
Right, musical chairs for electrons.
Ah, yeah, good analogy. Because of that, a quasiparticle near the Fermi energy has very few available states to decay into. So its lifetime gets longer and longer, the closer its energy is to that Fermi energy.
So the less excited it is, the more stable it becomes.
Exactly. At absolute zero temperature, theory says they live forever. This long lifetime, especially near the Fermi energy, is what makes them real enough to treat as particles. It validates the whole approach. It's the signature of what we call a Fermi liquid.
So Landau's theory, it's basically saying you can ignore the nitty-gritty details of every single interaction.
Pretty much.
You just bundle all that complexity into a few measurable numbers, like effective mass and lifetime.
Exactly. It black boxes the microscopic complexity. And you end up with a powerful predictor theory based on these emergent quasiparticles and their effective properties.
And this points to universality, different systems acting the same way.
Yeah, it's remarkable. Liquid helium-3, which is a fluid, and electrons in a metal. Completely different substances, right?
Totally different.
But at low energies, their behavior can be described by the exact same Fermi liquid theory. The only difference is the numerical values of their specific parameters, like their effective masses. It suggests deep underlying similarities in how complex quantum systems behave.
Okay, so you have this powerful framework. Let's go on that quasi-particle safari you mentioned. What kind of zoo have physicists found? It sounds like a whole hidden ecosystem inside materials.
It really is, and it shows how collective behavior creates this rich world of new players dictating the material's properties. Let's start with the fermionic ones, the ones that are sort of like modified electrons or their absences.
All right. First up, the classic. The electron quasi-particle. That's our dressed electron, right? The main guy carrying charge in metals.
That's the one, the archetype. Then, maybe even more important conceptually, is the electron hole.
The absence that acts like a presence?
Exactly. It's not a positron, not antimatter. It's just a missing electron in a sea of electrons. But tracking that vacancy is way easier than tracking all the other electrons moving around it.
And it behaves like it has positive charge plus E and positive effective mass.
Which is absolutely fundamental for semiconductors. Your phones, processor, solar panels, they all rely on managing both electron quasiparticles and holes. You can't understand them without the whole concept.
It's amazing how an absence becomes so central. What about the polaron? That sounds different.
It is. A polaron happens when an electron or a hole moves through a crystal lattice, and its electric field actually distorts the lattice ions around it. It drags this cloud of distortion, this polarization cloud, along with it.
So it's an electron plus its own self-induced lattice damage. Sort of, yeah. It's a composite quasiparticle. Electron plus its lattice polarization cloud. And because it's dragging this cloud, it feels heavier, its effective mass increases, and it moves slower, its mobility decreases.
Okay, that covers some key fermionic ones.
Yeah.
What about the bosonic collective modes? These are more like waves becoming particles, right?
Exactly. Like the phonon. That's the quantum of a lattice vibration. Think of it as a quantized sound wave moving through the crystal.
And they're important for heat.
Hugely important. They're the main carriers of heat in insulators. And maybe surprisingly, electrons bumping into phonons is the main reason metals have electrical resistance at room temperature.
So they cause resistance. But you also said they help superconductivity.
They do. In conventional superconductors, it's actually the exchange of phonons between electrons that creates the weak attraction needed to form Cooper pairs. A bit counterintuitive.
Wow. Okay, next up, plasmon. That's the electron gas oscillating.
Yeah, it's a coherent collective sloshing motion of all the free electrons acting together. Think of the whole electron sea jiggling in unison. And that's related to why metals are shiny.
Directly. Plasmons interact strongly with light, reflecting photons below a certain frequency, which is why metals have that characteristic luster.
Okay.
And there's a whole field, plasmonics, using surface plasmons oscillations trapped at the metal surface to manipulate light on scales smaller than its wavelength.
Super tiny optics.
Oh, cool.
And in magnetic materials, we have magnons.
Right, a magnon is the quantum of a spin wave. Instead of just one electron spin flipping, it's a propagating wave of spins tilting and precessing together.
Like the wave in a sports stadium, but with tiny magnets.
Huh. Yeah, not a bad analogy. And the exciting thing about magnons is that they carry spin information, angular momentum, without carrying charge.
Meaning less heat.
Potentially much less heat. No ohmic losses from moving charge around. That's the dream of magnonics, using magnons for ultra-low power information processing.
Okay, beyond those basic types you mentioned, bound states and hybrids, like the excitant.
An excitant is basically an electron quasiparticle and a whole quasiparticle that find each other attractive via the Coulomb force and form a bound pair.
Like a little neutral atom, but made of quasiparticles?
Kind of, yeah. It's electrically neutral overall. So it doesn't carry net charge, but it can carry energy through the material.
And that's important for?
Light emission and absorption in semiconductors. LEDs work because electrons and holes are injected, form excitants, and then the excitant recombines, releasing its energy as a photon light.
Ah, so excitants are key to LEDs and solar cells.
Absolutely. Solar cells do the reverse. Absorb a photon, create an excitant, then you need to break that excitant apart to get free charges and generate current lasers, too.
And if you couple an exciton strongly with a photon, you get a polariton, half light, half matter.
That's the one. It's a true hybrid quasiparticle, a mix of light and matter excitation. They have really weird and useful properties because they inherit traits from both sides.
This zoo is getting pretty diverse. Finally, what about superconductivity? You mentioned Cooper pairs.
Right. The foundation of conventional superconductivity.
Mhm.
Two electrons, which normally repel fiercely,
Yeah, like charges repel.
can actually experience a weak indirect attraction mediated by phonons, those lattice vibrations. They form a bound state, a Cooper pair.
And this pair acts like a single particle.
Yes. And crucially, it acts like a boson. And bosons can all pile into the same quantum state. This collective condensation of Cooper pairs is what leads to zero electrical resistance superconductivity.
Amazing. And what's a Bogoliubov quasiparticle? Sounds complicated.
It's the elementary excitation out of that superconducting state. If you try to disturb the condensate, you don't just create a simple electron or hole. You create a bogolon, which is a funny quantum mixture, a superposition of an electron and a hole.
It's just incredible thinking about how the material itself basically dictates the identity of what's moving through it. An electron stops being just an electron.
It really drives home how context-dependent these quantum properties are. Mass, charge, lifetime. They emerge from the whole system. They're relational.
Let's dig into that anatomy a bit more. We talked about effective mass, m star, being about the curvature of the energy bands, EK.
Right. It tells you the particle's inertia within the crystal. And because crystals aren't necessarily the same in all directions.
The effective mass can be different depending on which way the quasiparticle is moving.
Exactly. It can be a tensor. An electron might feel lighter moving along one crystal axis than another. It's anisotropic.
Wow, okay. And that negative effective mass idea, again, near the top of an energy band, that's how we understand the whole having positive mass and positive charge.
It's the key insight. The absence of something with negative effective mass behaves like something present with positive effective mass. Mind-bending, but mathematically sound and experimentally verified.
And stability lifetime. They need to live long enough to be treated as particles.
Absolutely. Their lifetime is limited by scattering. But near the Fermi surface, Pauli blocking suppresses scattering, making the lifetime really long. The decay rate actually goes to zero as the square of the energy difference from the Fermi energy.
So they become almost perfectly stable right at that ground state energy level.
In theory, yes, at absolute zero. This long coherence time is what makes the Fermi liquid theory work so well for many metals.
But not always. You mentioned strange metals.
Right. There are materials, often related to high-temperature superconductors, where this quasiparticle picture seems to fail. The excitations decay too quickly, they don't seem well defined. It suggests we need fundamentally new ideas beyond Landau's framework for those systems. That's a huge area of research right now.
And we can actually see these quasiparticles, or at least their properties. You mentioned ARPs.
Yes, angle-resolved photoemission spectroscopy. It's an incredibly powerful technique. You shine UV light or X-rays onto a material.
Knocking electrons out.
Exactly. And you carefully measure the energy and the angle at which those electrons fly out. From that, you can reconstruct their original energy and momentum while they were still inside the material.
So you directly map out that EK relationship. You can see the bands, see the Fermi surface.
You literally can. It gives you a direct picture of the electron quasiparticle states. It's stunning proof that these aren't just mathematical constructs. They reflect the real electronic structure. Other techniques, like neutron scattering or Raman scattering, can map out phonon and magnon dispersions too.
Okay, so Landau's theory works beautifully for many systems, but you hinted it breaks down sometimes, especially in systems with really strong interactions or weird topology. That's where things get even stranger.
That's where emergence goes into overdrive. Strong correlations or non-trivial quantum topology can fundamentally transmute the properties of the excitations. We're not just dressing up electrons anymore. We're potentially changing their fundamental nature within the material.
Transmuting them, like changing their charge.
Believe it or not, yes. The most famous example is the fractional quantum Hall effect, FQHE.
Okay, what happens there?
You take a very clean 2D electron gas, cool it way down, put it in a massive magnetic field, and you measure the Hall resistance, basically, the voltage across the sample divided by the current flowing through it.
And normally that resistance changes smoothly with magnetic field.
Or it shows steps at integer values related to fundamental constants. But in FQHE, you see these incredibly flat plateaus where the conductance is quantized to fractions, like 13, 25, 37 of the fundamental conductance quantum.
Fractions. So the things carrying the current act like they have fractional charge, like 1/3 of an electron's charge.
That's exactly what it looks like. It's mind-blowing. The electrons themselves still have charge E, of course. But because of the intense interactions in the magnetic field, the elementary excitations and the things that behave like particles carrying the current act as if they possess fractional charge, like E3.
How is that possible?
The leading theory involves composite fermions. It's like each electron grabs hold of some magnetic flux lines, forming a new composite entity. This composite fermion effectively feels a different magnetic field, and the resulting quasiparticles carrying the current end up with these fractional charges. It's pure emergence.
And this leads to things called anyons, neither fermions nor bosons.
Precisely. In 2D, unlike 3D, you're not restricted to just bosons or fermions. When you swap two identical anyons, their wave function picks up a phase factor that can be anything, not just +1 bosons or -1 fermions. These FQHE quasiparticles are experimentally verified examples of anyons.
Wow. Okay. And then there's topological matter. What's the idea there?
The idea is that the overall shape or topology of the electron wave functions across the whole material can guarantee the existence of special states, usually on the edges or surfaces.
And these states are somehow protected.
Extraordinarily robust. Because their existence is tied to this global topological property, they're immune to small local imperfections or dirt in the material. This protection is incredibly appealing for technology.
Like what kind of protected quasiparticles?
One famous example is the Majorana fermion.
Yeah.
Predicted theoretically long ago, it's a particle that is its own antiparticle.
Its own antiparticle. How does that work?
Think of a regular fermion, like an electron, as being made of two distinct parts. In these special topological materials, specifically topological superconductors, theory predicts you can spatially separate those two parts. You get a Majorana zero mode at one end of a superconducting wire and its partner at the other end. Each mode is, in a sense, half a fermion.
And these are quasiparticles emerging from the superconductor.
Yes, emergent quasiparticles. They aren't fundamental particles, as far as we know for sure yet, but they appear as stable, zero-energy excitations in these specially engineered materials. And their unique nature, plus that topological protection.
Makes them exciting for quantum computing.
The holy grail, potentially. Because they're their own antiparticles and obey exotic non-abelian statistics, braiding them around each other could perform quantum computations in a way that's intrinsically protected from errors. We're basically trying to create designer vacuums inside materials to host these incredible emergent entities.
It really is like science fiction becoming reality. From a mathematical simplification to particles with fractional charge or particles that are their own antiparticles, it's just amazing.
And this progression shows how technology really pushes forward by gaining finer and finer control over this hidden world of quasiparticles. Every deeper insight seems to unlock a new capability.
So how does this quasi-particle world actually impact the technology we use every day?
Oh, fundamentally, the entire semiconductor revolution built on quasiparticles.
How so?
Every single transistor in your computer chip, in your phone,
Yeah.
it's essentially a valve controlling the flow of electron quasiparticles and whole quasiparticles. We learned how to create them, move them, block them. That mastery is the foundation of all modern electronics.
And things like LEDs and solar cells.
Governed by excitons. Remember them,
Yeah.
the bound electron-hole pair. In an LED, you inject electrons and holes, they form excitons, the excitons recombine, and boom, light comes out.
And solar cells run that in reverse.
Pretty much. Light comes in, creates an exciton. Then the trick is to efficiently split that exciton into a free electron quasiparticle and a free hole quasiparticle, which then generate the electrical current. It's all exciton dynamics.
Okay, what about future tech? Where are quasi-particles taking us?
Well, there's spintronics, using the electron's spin instead of just its charge. And even more futuristic, magnonics, using those magnon spin waves.
It's a stadium wave of spins.
Right. The big draw there is potentially ultra-low power computing, because moving spin information around doesn't necessarily involve moving charge, so you avoid a lot of the heating that limits current chips.
And plasmonics, too, using those surface electron jiggles.
Yeah, manipulating light at the nanoscale.
Yeah.
Because surface plasmons can confine light much tighter than its wavelength allows in free space, you can make incredibly tiny optical circuits, super sensitive sensors, maybe even things like invisibility cloaks, using metamaterials built with plasmonic structures.
And quantum computing seems like the ultimate quasi-particle playground.
It really is. Many of the leading approaches use superconducting circuits.
Relying on Cooper pairs.
Exactly. The macroscopic quantum coherence of billions of Cooper pairs acting as one entity is what allows superconductors to be used for qubits. Devices like Cooper pair transistors are used to manipulate and read out these quantum states.
But the ultimate goal is that topological quantum computing using Majoranas or Enneagens.
That's the dream for many. Storing quantum information non-locally in the topology of how these exotic quasiparticles are arranged or braided.
Because that makes it robust.
In theory, incredibly robust against local noise and errors, which is the biggest killer for current quantum computers. Performing computation by literally braiding the paths of these Enneagens. It's a radically different approach, but incredibly powerful if we can realize it. Major companies and research groups are pouring resources into this.
So really, the next time you pick up your phone, you should remember there's this whole hidden universe inside.
A bustling ecosystem of quasiparticles doing all the work.
It just makes you wonder, if this concept is so powerful for understanding materials, what does it imply about, well, everything, about reality itself?
That is the big provocative question, isn't it? We see quasiparticles emerge from a complex medium, like electrons in a solid. But then you look at fundamental physics, quantum field theory.
Where fundamental particles are excitations of quantum fields.
Exactly. A photon is an excitation of the electromagnetic field. An electron is an excitation of the electron field. It sounds suspiciously similar, doesn't it?
It does.
Are you suggesting?
Well, what if the vacuum of space isn't truly empty? What if it's some incredibly complex medium we don't fully understand? Could it be that the particles we call fundamental are actually just the low-energy quasi-particle excitations of the vacuum itself?
So an electron's mass might just be an effective mass given to it by its interactions with the vacuum field.
It's a profound analogy. It suggests the lessons we learn from condensed matter about emergence, collective behavior, renormalization, new kinds of excitations might be clues to the very fabric of reality. Maybe the line between fundamental and emergent is much, much blurrier than we usually think. Wow. That's a lot to chew on. What if we are just complex quasi-particles of the universe?
It certainly makes you think. It highlights that there's always another layer, always more to understand. The success of the quasi-particle idea is a testament to the richness of collective phenomena.
Well, we hope this deep dive has maybe shifted your perspective a little, giving you a new lens to look through at the world around you, right down to the metal and silicon that powers our lives. Keep asking questions.
Absolutely. There's always more to explore.